Deep learning is useful, that artificial neural nets are useful and they work. What I want to convince you of is that those are still algorithms and they do only as much as we designed them to do. Why would that be important? So we've seen various examples of algorithms. They do various tasks, they're good at it, that they excel at it, they're better than humans. If you were an algorithm and you were asked to recognize a face, how would you do that? Any ideas? Well, it's not so complicated, right? A face has a mouth, a face has a nose, it has eyes and eyebrows, and it pretty much looks like that, right? This must be what you imagine. But it is not a joke. This is actually a 3D printed mask that was used to trick the Apple's secure Face ID recognition last year. And it took 10 days to trick. So it seems like we have a bit of a problem. We use those algorithms, and I don't want to say that you shouldn't use those algorithms at all. That's not what I mean. Apple has fixed it. But in principle, it seems like we have a problem. Because we see the results of the algorithms, we see that it makes sense, and we automatically assume that the decision is also based on the cues that we would base our decision on, which may or may not be true, and sometimes it's actually not true. Why would we assume that, though, and why would that be even interesting for a computational neuroscientist? It's interesting because neural networks are somehow loosely inspired by the human or mammalian visual system. So the way they work is that they look for we're too early. Sorry, haven't seen that yet. So the way that these neural networks or convolutional neural networks work is that they first look for edges, they scan the image for edges, they integrate those edges, then they make a shape out of it, they look for the shape all over the picture, they learn that this is an object, look for this object, and so on and so forth, and then we're at the very complex and abstract recognition, which is what happens in humans. And there is this hierarchical architecture to this deep convolutional neural network that seems to be very powerful. It works for us, it works for the networks, and yet it seems like the workings is tiny bit different. But there are people who are really interested in comparing those two, psychophysicists, and in this particular branch of science, we try to sort of take a look at what does the network see in an experiment somehow similar to the experiments that we do with humans. So we present some images, we look at what's going on in the network, we look how the network is responding, and we try to make our mind about it somehow. So such an experiment, or generally using a network, means that we have an image, we pass it through the network, we get a probability distribution over a set of labels. Those are normally a finite set of labels because it really belongs to a data set. We get this probability distribution. This is one thing that's important for us. Another thing that's important for us is an accuracy. Top 1 accuracy if the first prediction of the network is the true prediction. Top 5 accuracy if the true prediction is within the 5 best guesses. And the accuracy we actually average over a lot of pictures, so we get a percentage. Like, for example, a network can be 88 and 5% accurate in comparison to a human that is way more accurate on this particular data set. But as an 88 is not too bad, and this is the network that I used for some of my studies. Only that I didn't ask it to take a look at regular images. I did a very simple manipulation, so the images were masked. And as you can see, I guess you can see it in this particular picture, up to a particular level of masking, this is actually 50% of the image that is occluded. We're actually still quite good at recognizing the content of the image, especially if it's in the middle, but in general, this is a doable task. Now, how do network perform on it? Apparently not that good. So if you take a look at 50% here, and this is just a square occlusion, meaning that the edges are occluded, and actually the network is losing quite some accuracy, like 15%, let's say. This is way more than we would intuitively think as humans. Now, it gets even worse if we use a square mask, and it gets even worse if we occlude the middle. But also the edges only. This is an interesting result. And why would that be? So we hypothesized that perhaps the network actually doesn't know that we ask it to look at something that's occluded. We taught it to recognize edges. What we pretty much do here, we introduce extra edges to the picture, and the network has no information that this edge is not an inherent piece of the picture. So we train another network, and we allow it to look at smaller picture this time, because the other one, like, well, it's tiny bit limited. There is only a big picture or a small picture that we can recognize. We try to get rid of it. We get rid of it on a bit of accuracy loss, but we're able to make a more flexible experiment. So we do that. We add these cuts, and now we're going to contrast the performance of the cuts versus the masks. And what we can see here is that, in fact, the cuts, or the crops, as I named it there, are way easier for the network to recognize. So it seems like, in fact, the network with some extra occlusions doesn't make sense out of what an occlusion could be. Right. But the performance drops at the end. So here we are at the tiniest pictures that the network can look at. This is 32 by 32 pixels. And the performance is not really good. Now the question is whether the performance is not good because this is too small to recognize, or are we just looking at the bad piece of the image? So I repeated the experiment and took every single 32 by 32 piece of the image and evaluated my network on that, and then tried to arrange those images in an order such that I want to see the best ones, the ones that network recognizes the most. And this is what we've got. Oh, the colors here are not that good. But what you can see here is for the 25 best images for the class of Fox, 25 best images for the class of All, and 25 best images for the class of Beer Bottle. Those are the classes in the general data set the networks are trained on. And the fun fact is that the foxes and eyes of the Alls and beer bottles, they all seem to make sense. So actually, in this setup, the network actually looks at the cues that also seem to be important to humans. So then we ask another question. Okay, so maybe it's actually not that important that the network gets all of the information within the image, and maybe it's enough if we only allow it to look at this 32 by 32 pieces of the image, so we train yet another network. And it's quite not as good, which is surprising, because before it looked like the network can make sense out of the small pieces of information as well. So I tried to test it again. And how can we test the importance of the global information in the image? How can we test the compositionality of the network, or like how important the compositionality of the image is? Well, we asked the network to look at shapes. So with original colors, all of that is quite easy to recognize. But if we only take shapes, and if those pictures are big, then the network that can only look at tiny pieces of it can only see black, white, or borders. And it turns out that while all of the networks that we have tried suffer quite drastically and underperform in this condition, the network, the last one, that cannot integrate all of the global information, is the one that suffers the most. So it seems like this missing percentage in our networks comes exactly from that, from the lack of recognition of the shape. And this is actually the last experiment that I wanted to explain to you, as I think that, well, 10 minutes is not enough time for more, although I'll be more than welcome to take questions. Right, oh no, I'm sorry, there's one more. Right, so even better. So this last network, it turns out what it does, it's only able to recognize very simple shape. So this supports against this intuition that 32 pixels is just enough to recognize edges and stuff like that, but not more, like not enough to recognize a tiger or a lion, and those are not very complicated shapes. And now with this, I'm 100% sure that this is the last experiment. So let me leave you with those few points. And first of them is that convnets don't exactly do what we do. So they are not humans. They don't process information like humans do. They're just algorithms that do what we taught them to do. And it's not too bad either, because we know that those algorithms tend to work, and probably after the event, there'll be photos, someone will put them on Facebook, you'll get notifications with your faces in it. That's okay, it works. We just need to know the constraints, and for very particular applications, it's just good to know what you're working with. It's good to test the border conditions, and it's good to improve upon it. So yeah, with that, I hope that I gave you some insight into the inner workings of neural nets. Import them to your browser with Piotr's OpenAI, or no, that's not. Import them to your browser, have fun, recognize faces, but just know what's in there. Thank you.